In this lecture, let us discuss about the Fourier series. Fourier series analysis. And this we will be covering for continuous time signals. So we will postpone the discussion on Fourier series for discrete time signals for now. So suppose we are having, and this Fourier series analysis is a tool which is applicable only for periodic signals. So for non-periodic signals, we have another tool which is known as the Fourier transform, which we will discuss later. So what is meant by a periodic signal? Suppose I am having a signal of this nature. Let us say we are having some train of rectangular pulses which is separated by, let us say, let this entire width be t, which is the time period of the signal. So this is x of t and this is your time axis. Now when we are having a signal of this nature, this signal can be decomposed into a DC component and and sinusoidal components. The sinusoidal component will have a component with the fundamental frequency, and then it will have higher order harmonics. So what I am saying is, so this x of t can be written as a DC component plus a cosinusoidal term. Now this omega d is nothing but omega is equal to 2 pi f, and that f is nothing but 2 pi divided by t, and this t is nothing but the time period of this signal. Now this x of t can be thought of as a DC component plus cosinusoidal components. The third term is a cosine term which could have a frequency which is twice the fundamental frequency. The fundamental frequency is omega, so the third term will have a frequency of 2 omega t. Then we have the fourth term which is 3 omega t, so on and so forth, plus b1 sine omega t, b2 sine 2 omega t, so on and so forth. I have written both the sinusoidal term and sinusoidal terms, and there are amplitudes for each of the terms. A1 is the amplitude for the first fundamental. The second harmonic is having an amplitude of A2 for the cos term. Similarly, for the sine term, we are having B1 as the amplitude for the fundamental, B2 as the amplitude for the second harmonic, and so on and so forth. Now, these the amplitudes that I have just mentioned, that is A1, A2, A3, are called Fourier series coefficients. Now, what is the need for us to actually study this analysis? Now, in our circuit theory, we know that we have studied, so let us say we are having a circuit like this, something like this. Now, the question is, what can be the voltages, the input voltages? What kind of shape or what kind of quantity the input voltages could be? Now, ideally, the shape of the input voltage can be anything. It can have any shape. Okay, so you need not have a defined shape. Let us say we are used to actually seeing a voltage of this nature, which is a DC quantity, or maybe a quantity like this, which is a sinusoidal. So in our circuit analysis, we would have either used this type of signal or this type of a signal. So, and the question is whether can't we apply a signal of this nature? Now we can. The problem is when we are studying in our colleges, in our when we go to when you go to our work, say when I'm joining some company which is dealing with electrical equipments, there you may come across the circuits being excited by a voltage of this nature. Very often than not, in switch reluctance motors, you may have a voltage of current of this nature, something like this. So, but in our in our undergraduation, we are mostly used to doing analysis only with two types of waveforms. One is the DC waveform, the other one is the sinusoidal waveform. But then, how suppose if you want, if you have to um, analyze for a wave shape as shown here, then how can we go about doing it? This type of wave can be applied to a circuit like this, but we have not learned any tool which can help us to actually analyze what is going to be the current and what is going to be the voltages across the components. However, we have some very important tool which is known as the superposition tool that we have studied. Superposition theorem, which states that suppose we apply say 2 or 3 voltages of different shapes, maybe a DC voltage or AC voltage, and AC voltage itself we are having a different wave shape. So let us say we are having V of t is equal to some DC quantity plus 10 sine 10t plus say root 2 times 100 times 100 into cos say 20t. Now when we are having a signal, if this type of a signal will have to used to be applied to a circuit like this, then how do we go about doing analysis? All that we need to do is we need to first find out what is the response due to 10, and then find out what is the response due to this. This is a steady state sinusoidal analysis. So what is the response due to this term, and then finally we have to find out what is the response. Then add up all the responses, we will get the total response. So the superposition theorem in fact helps us to do it. So when you are having a signal of this nature or a signal of this, maybe a signal of this nature, a pulse train, rectangular pulse train, this is periodic, but this signal as such cannot be applied to the cannot be used for analysis. So what we have to do is we have to convert this into a suitable form where we have only DC quantities and the sinusoidal quantities. So that there we take the help of Fourier series analysis. So this type of a signal can be converted into a into a uh, into a DC term plus sinusoidal terms, and then the response due to each of the term can be found, and finally the total response can be found by adding up all the responses. So this is one reason why we want to study the Fourier analysis. Okay, so we have introduced the Fourier series representation. So x of t can be represented as a naught plus a1 cos omega t plus a2 cos 2 omega t plus it goes on like this, and then finally we have b1 sin omega t plus b2 sin 2 omega t. It goes on like that. Now this type of Fourier series representation is known as a trigonometric Fourier series representation. Metric Fourier series representation. Now we have to find out what is the A0 and the Fourier series coefficients. So given a x of t, suppose I take the same example, same wave shape. We are having a train of rectangular pulses which is separated by a time period t. So the total time period is t. So let me, this one will be t by 2 and this will be negative of t by 2. So we have, so the trigonometric Fourier series is what this one is. So let us again write that a of t is equal to a naught plus summation of 1 to infinity a n cos n omega naught t plus dn sin n omega naught t. Now a naught can be found by this following integral, that is over one time period we have to integrate between limits t by 2 x of t dt, and similarly b1 can be found, an can be found by the following formula, minus t by 2 to plus t by 2 over one period we are integrating it. So x of t cos n omega naught of t dt. So omega naught is nothing but 2 pi by t, where t is the time period of the pulse, the rectangular pulse train, and it is also known as the fundamental. So the fundamental can be obtained from the periodic signal itself. So again bn is equal to 2 by t by t x of t cos sin, sorry, it's sin n omega naught t dt. So let us try to take an example. Let us try to find the Fourier series representation for the signal that we have taken it as an example. Let us say we are having a signal, let this be t by 4, and we are having t by 4, and let this be t by 2, then we have t by 2. So again the pulse repeats itself on either side. Now we have to find x of t, that is a Fourier series representation for the signal. That is, we have to express this signal in terms of DC terms and sinusoidal and cosinusoidal terms. Now if you observe closely, if you look at the symmetry conditions, if you look at this signal is having a even symmetry. When you are having an even symmetry, we will have only the cosinusoidal terms, that is the an terms, and not the bn terms. So we will try to evaluate both an and bn, and then we try to justify the statement that we have made that a signal of this nature will have only an terms. Okay. So first let us try to evaluate a naught, which is a DC term. It's nothing but 1 by t by 4 t by 4 x. Let us the amplitude, let it be 1, so for the time being. So x of t dt, so this I can write as 1 by t by, let's say I will put t by 4 because the signal is present only between negative t by 4 and positive t by 4. So I should have put 2, but from negative t by 2 to negative t by 4 there is no signal at all. The signal value is 0. So I have to put it as 1 dt. So when I evaluate this, what I will get, say 2 t by 4. So this t and this t will cancel, so I will get half. So my a naught is half. That is, a DC term is having a value of 0.5. So it will be okay. So let me evaluate the next one, which is the an, which is nothing but 1 by t minus t by 4 to t by 4 x of t cos n omega naught t dt. Now we have to evaluate this. So if I try to evaluate this, so let me rewrite here. An is equal to 1 by t by 4 t by 4 x of t cos n omega naught t dt. So again I will write here omega naught is nothing but 2 pi divided by the time period of the pulse. So when index of t is 1 here, in this case it is 1. So this will be equal to t by 4 cos n omega naught t dt, and if I evaluate the integral, it will be sin n omega naught t divided by n omega naught. So let me put the limits. Let me apply the limits. If I apply the limits, what will happen? Omega naught into sin n omega naught t by 2 t by 4 minus sin n omega naught negative t by 4. So it will be like this. And if I evaluate this further, I will end up getting something like this: 2 times sin n omega naught t by 4. So let me make a note of it so that I can take this to the next page. So it is 1 by 2 times sin n omega naught t by 4. So let me go to the next page now. So it is 1 by n naught 2 times sin n omega naught t by 4. Now you know that omega naught into t is equal to 2 pi. It is a known fact that anyway, you know, we know we have defined it 2 pi by t. Omega naught is 2 into 2 is equal to 2 pi. So you will have anyway, I think we are missing the, we'll go to the previous page. I think we need to put a 2 by 2 here, 2 by t here. We have a 2 by t, 2 by t. So this into 2 by t. So this, substituting the values, we will end up getting n times 2 pi into 2 times n times 2 pi divided by, so it will be 2 divided by n pi sin n pi by 2. So when n is equal to 1, you will have, the value will be the an, this is an. So let us put, let's make a table. So we have n here and an here. So for 1 it will be 2 by pi sin pi, which is nothing but just 2 by pi. When n is equal to 2, it will be 2 by 2 pi sin pi, which is 0. So when it is 3, you will have 2 by 3 pi. You will have 3 divided by, which is nothing but negative of 2 by 3 pi. So an values, we have found the an values. So let us go and try to evaluate the bn values. So bn values is nothing but 2 by t by 4, and that is 1 times sin n omega naught t dt. So when you evaluate this, you end up getting my negative cos n omega naught t divided by omega naught, and this t by 4. So it will be 2 divided by n 2 pi negative cos n omega naught t by 4 minus cos n omega naught minus t by 4. So you can very well see this, that the terms that is inside the bracket, terms inside the bracket evaluates to 0. To pi minus of is t n omega naught pi by 4 minus cos n omega naught t by 4. So this will evaluate to 0. So by our Pn is equal to 0. So An, we found the An values and we found the Bn values. So An values are for the first harmonic it is 2 by pi, the third harmonic it is 5, fifth harmonic it will be like this, so on and so forth. So let us summarize. So we had d, so x of t is equal to half, which is a naught, plus a1. a1 is nothing but 2 by pi cos omega naught t minus 2 by 3 pi cos 3 omega naught t plus 2 by 5 pi cos 5 omega naught t, goes on like this. So this is what we get for x of t. So this is the answer. So this is how the Fourier series representation is done for a periodic signal, but it is not sinusoidal. So this is one type of representation. So another type of representation of Fourier series is called cosinusoidal representation. So let us cosinusoidal representation, cosinusoidal representation of Fourier series. So what is a cosine? What is meant by a cosinusoidal representation? So let us take the trigonometric representation itself. So we have x of t is nothing but a naught plus. So we have 1 to infinity a n cos n omega naught t plus Pn sin n omega naught t. So I can actually do some manipulation. Let me multiply and divide with this quantity. When I do that, I end up getting like this. Plus Bn divided by root of An squared sin n omega naught t. So let us define cos phi as An divided by root of A n squared plus Bn squared, and let us define sin psi as negative Bn divided by root of An squared plus Bn squared. So the x of t can be written as a naught plus an squared plus bn squared 1 to infinity cos psi plus omega naught minus sin phi sin n omega naught. So combining this, I think we can write it as an squared plus bn squared n is equal to 1 to infinity cos n omega naught plus phi. So your phi is nothing but tan inverse of negative bn divided by an, or it can be written as negative tan inverse of bn by an. So this is your bn is actually, say when you're having a, let us say we are having an and j and bn, let us say the axis for bn is actually j times bn, it's imaginary. So negative is actually we have a negative term, negative bn will be like this is negative bn, and you have an. So this is nothing but, so you're going in the negative, the clockwise direction. When you go in the clockwise direction, it is always negative. So when you go in the clockwise direction, so the let us say this phi. This phi is nothing but tan inverse of magnitude of bn and divided by magnitude of an. But since we are going in the negative direction, I have to put a phi minus. So psi is negative tan inverse of bn by an. So this is yet another representation. So plus an a naught. This is yet another representation of Fourier series. So the Fourier. So we have seen so far two types of representation. One is the trigonometric Fourier series representation, and the other one is the cosinusoidal Fourier representation. So the next type of representation is the complex Fourier series representation. So how to represent the x of t? X of t can be represented as minus infinity to plus infinity Cn e to the power of j n omega naught t, where omega naught is the fundamental frequency 2 pi divided by of the signal. We can take the same signal itself, the pulse string, the rectangular pulse string itself, we can take it. And for that, the time period was found to be t, so omega naught will be 2 by pi t. So I need to evaluate the Fourier series coefficient, which is nothing but 1 by t minus t by 2 plus t by 2 x of t e to the power of minus j n omega naught t dt. So this is another representation of Fourier series. So we have seen three different type of Fourier series representations so far. Let us deal with some symmetry conditions. So you making use of the symmetry conditions, we will be able to simplify our analysis. Suppose if we are having a wave, something of this nature. Let us say we are having a wave or a signal which is of the following. It is having the following. Now a signal of this form now we can very well observe the signal. Let us say this is t by 2 and there is another t by 2. This has to be t by 2 because after this the wave shape is actually repeating itself. Now if you take a point, let us say at some distance, Let us some distance, let us say some distance t naught on the positive direction, and again you take another just the same distance on the other direction, you will find the values are same. A wave having displaying this type of a characteristic is known as an even function. So what is this is an even function. Okay. Now it has certain characteristics. Let us just be x of t. Now if you flip this along the y-axis, flip this wave, that is find the mirror image of it. You will find that the mirror image will be exactly the same as x of t. If you try to flip it, you get the same wave shape, that is x of negative t. So x of positive t will be equal to, when you're analyzing, when you're doing a Fourier analysis for this type of wave, it will become it will be clear, or it is evident that it will have only the cosinusoidal terms. It will not have the sinusoidal terms at all. So this um, a wave having this type of behavior is known as an even function. So what is an odd function? Suppose we are having a wave which is something like this. So this is negative t by 2 and this is positive t by 2. Here if you flip this wave, then x of t will be equal to negative of x of negative t, which just means it's an odd function. When you are having an odd function, then you will have only sinusoidal terms. Only sinusoidal terms are present. So in the previous case, you may have a naught term. In this case, you have the a naught term. In some cases, you may not have, but you will have, but you will have an terms. Bn terms will be equal to 0. Okay, this we have seen in one of our in the previously worked example. So in this case, Bn will be present. A naught and An will be absent in this case. So in this particular case, A naught will be absent. But we need to check whether every case where the function has to be is odd, A naught will be present or not. So I think yes, A naught will be absent in all the cases. Okay. So both the DC term will be absent, only the Dn terms will be present. Right. So there are certain symmetry. We'll be actually be touching upon the next type of symmetry, which is known as the half-wave symmetry. And when you have the half-wave symmetry, in fact, the wave that we have discussed has a half-wave symmetry. Let us say we are having a. Let me draw the same signal that we have learned previously. Let us say we are having a signal of this nature. Now, let us say x of t. Let me shift this signal, it gives t by 2 and this is negative t by 2. Let me shift this wave by, if I shift this wave by shift by t2, that is delay in the positive direction, then you will have a wave something like this. So it is t minus t by 2. When I flip this along the x-axis, suppose I flip this wave along the x-axis, I end up getting, so I flipped it, so negative of t minus, which means x of t is equal to negative of t minus. Now when a signal exhibits, has this type of characteristics, then this is known as half asymmetry. When a signal has an half asymmetry, it has only odd harmonics. It does not have even harmonics. That is, n will be equal to 1, 3, 5, 7, 9, so on and so forth. So with this, let us stop now. Let us continue with further concepts on in Fourier series analysis in our next video. Thank you.